Okay.
At the very least, this is going to be very entertaining.
Oh man.
We'll just do shadow stuff all the time.
Everyone's like,
Shut up! I know you're not gonna be here because Andre asked you to leave.
Sammy,
just go away.
I may not be there physically, but my heart is with you all the time.
yeah.
That's what bro said.
Yeah, I know.
Oh.
Oh my god, what is that?
Can you not doing that?
Is that a caterpillar?
Okay,
This is
This is
You're
loser.
saying be serious, and your title says loser.
so can I start now?
Sure.
Everyone's ready?
recording.
Okay, yeah, of course. So today so it's my week to present this lab technique, and my lab technique is laser here. But as you can see, I put loser in the title for some reason, and we're gonna cover this in the later part of this presentation. So laser. So I'm gonna briefly go through some of where the name of laser coming from, and some important historical milestone of lasers. Then I'm gonna talk about how laser works, or the structure of laser a little bit. Then I'm gonna address a few types of lasers that I think is important, and I'm gonna talk about the various use of lasers. So, what is laser? Laser is a shortened for light amplification by stimulating emission of radiation, and this term was coined by this Golden Good. And laser, why I talk about laser? Because laser is the most important optical device in the past 50 or 60 years. And a fun fact about laser was that it used to be called loser because it was the shorthand for light oscillation by stimulating emission of radiation. And I'm gonna briefly talk about the amplification part and also the oscillation part of laser. So a little bit history of laser. So in 1917, Albert Einstein actually laid foundation. Albert Einstein actually laid foundation for laser by proposing this stimulate emission theory here. Then in 1950s, there are scientists in Bell Laboratory actually working on laser. This Charles Downs and this Arthur Shine here, they work together build the first laser, but it's called Maser. And the Bell Laboratory actually fired the patent for Maser. The reason it's called Maser is because the laser actually emits at the wavelengths around microwave or radio wave. But for the later lasers like X-ray laser or ultraviolet laser or the visible light laser, they are just called something laser. But this is one exception here. And in 1960s, Thomas Mayman actually produced the first laser using this ruby roll here. And we're going to talk about the laser structure and the mechanism using this ruby roll laser as the prototype, because it's a simple 3-level laser and it's easy to understand. I hope you can actually appreciate this thing a little bit. So, what makes, before we talk about the mechanism, I have to address the major difference between the incandescent light, the normal light bulb, or the sunlight, versus laser. Why is laser different? So first off, laser is monochromatic, which means it only emits light at a certain wavelength, as you can see here in the picture. But when you have sunlight or the light emitted from light bulb, and you have a prism here, at a right angle, you can actually split the light to different wavelengths. So this one is polychromatic here. And the laser light is coherent, which means the waves are constructive, so it can actually, the waves are in phase, so it can actually give it's the premise to have this enhanced intensity, because your different waves can really add up to each other. And also laser light is polarized. It's some first year organic or physical background if you have. So the laser light only oscillates at one angle, not the other one. It's different from this sunlight or anything. And laser light is directional. As you can see from my laser pointer here, when you shine a light on the wall layer, you can only see one dot. But if I hold a light bulb, you can see a whole large area of this brightness. And of course, laser is high energy. We use it for educational purpose. We use it for industrial purpose. And the most fundamental thing is laser is stimulate emission rather than spontaneous emission here. So laser, how laser works? Laser works based on three main factors. First of all, energy pumping and stimulate emission. Second of all, the population inversion here. And third of all, optical resonator is also a very essential component for this thing. And we're gonna use Ruby laser as a prototype to talk about all these mechanisms here. This is just the structure here. We can see it's not very obvious, but it has a circle here, and it has a ruby roll. And here we go. So what is stimulate emission? So we know from physical chemistry, like first year level, when you shine the light on an atom or any object, and if the energy, incident energy is exact the energy difference between the E2 level, excited level, and the ground state energy level, it can excite this atom to a higher energy level. Here, it's called absorption. And if we, of course, according to thermodynamics, this high energy level excited state cannot last for very long, so it must undergo realization to release this excess energy. So it will go spontaneous emission naturally, and it can release its energy as either light or heat. So these are the two observable phenomena in nature, but we're talking about stimulate emission. When you shine a light, when you emit a photon on an atom or object, it's already excited. This photon will just be transparent, bypass the atom here, but it also triggers this atom to undergo realization. So, sorry, I have to point out that part here. So this emit photon here can go any direction. It can go here, or here, or here, or here. So it's not directional. As for the stimulate emission here, when you shine a photon, it actually got, the photon got transpassed this atom, and the atom also emit a photon. So instead of emit one photon, it emits double it. So it's called stimulate emission. And also this light is directional here. And that's the stimulate inversion, stimulate emission. And we're going to talk about population inversion.
Can I ask a quick question?
Yeah, sure.
Oh, what do you mean it's stimulated? I'm just a bit confused. Do you?
So you have to have something to excite it, let's say, or to have an outside stimulate in order to have this excited atom to go undergo realization.
Oh, okay. So, okay, yeah.
What's the difference? Go ahead.
Well, how do you make sure that the spontaneous emission is natural? It happens naturally.
We're gonna talk about this cover in the population inversion part. How can stimulate emission occur? Okay, so according to Boltzmann equation here, so the number of atoms at excited state is N2, and we define number of atoms at ground state as N1 here, so that naturally at a thermal equilibrium or a constant temperature, according to Boltzmann distribution, that N1 is always less than N2. N2 is always less than N1 in order to have a stable condition here. So if N1 is bigger than N2, and you shine a light or emit photon on this system, it doesn't undergo spontaneous, it doesn't go stimulate emission. What it will do is excite some of the atom to a higher energy state. And when the number of atoms N1 equals N2, when you shine a photon, it actually just bypass this system here. So we call this thing as optical transparency, or transparent. The photon just being transparent to this medium here, but only when the N2 is higher than N1 here can the stimulate emission occurs. And because the N2 number of N2 is higher than N1, it's the extraordinary thing. It's so we call this thing, it's opposite from the natural population distribution. We call this thing population inversion, and therefore population inversion is an essential step in laser. So how to create a population inversion here? Population inversion is really hardly can be achieved naturally in a two atomic energy level system here. Sorry, yeah, this part didn't come out as I expect due to this thermal equilibrium, and therefore the maximum you can do in a two-level system is the optical transparency, which is N1 equals N2, and therefore people have to, in like 60 years ago, people think outside the box. So instead of two-level system, they found this three-level system or this four-level system. So by having this kind of system, can the population inversion occur, and can the stimulate emission occurs. So the basic idea here is you have this E1, and you excited these atoms to a higher energy state, and you quickly undergo this realization to a metastable state here. So it's like holding it back for a few seconds. So at some instance, the number of atoms here will be higher than the number of atoms here. So it's the population inversion can occurs. And this is the first laser, ruby laser. With this, the ruby has actually this structure of three-level systems, and as we can see in our daily life examples, we have these self-luminant stones. If you put those stones in some very dark room and can emit light, because naturally those atomic structures have some really impurity, so it actually create the metastable state there, because it's the difference due to this structure. And these days we don't use three-level system laser that often because it's not efficient. In order to create a population inversion here, you have to at least excite like 50, at least more than 50% of atom to a higher state. And these days we use more often with this four-level systems or multi-level systems for our laser beams. So the last part of the working mechanism is the optical resonator here. So this is a ruby laser, and we can really take a close look of this thing by I draw this thing. This assembles the ruby rod here, and we have we have these circles that created to give this energy investment. So we call energy pumping here. You can have different ways to pump energy to this ruby rod to stimulate, to excite the ruby atoms inside this rod here. And as we can see, we have two mirrors here. One has the reflective index 100%, and one has this refractive index of like 99% or 99.9%. So what we do is we stimulate this ruby here, and suddenly we turn off the switch, and then these excited atoms will undergo realization and emit these photons. So if you emit this way, it just go out, it doesn't get amplified. And go this way, it doesn't go amplified. Only when the photons that gets emitted horizontally, it can get amplified by going this way, and on the way it gets the photon transpass other excited photons, other excited atoms. So it's like a domino effect, and it triggers these stimulate emissions to occur. So by doing this, it reaches this part of mirror, and it's like a ping pong kind of thing. It bounces back forth. So we can see it bypass a lot of these excited atoms, and they got this constructive waves together. The light actually gets amplified, and because of these two mirrors, it also got oscillate in between, and eventually reach the threshold and goes through this partially refractive surface here, and have this very concentrated laser beam. So this is how laser works as the prototype Ruby laser, and we can see some further more complicated laser in my last few slides.
So does that work by wave addition?
Yeah, constructive waves.
So then, like, the length of the laser would be really important. The length of the Ruby would be important, because if you're off by a bit, then you could get destructive interference, like, rather than constructive, right?
No, because let's see. I'm not quite sure about that, but the wavelength of those, the length of this Ruby roll, the material is well designed in order to have this constructive wave. And let's see. So by changing the material here, we can have different wavelengths. So you can have this red laser beam, blue laser beam, or other stuff by changing the material here. So we're gonna do the classification of laser. Laser can be sorted by time. So we have pulse laser or continuous laser. It's literally just time difference. And by material, so we have gas phase laser, we have liquid phase laser, we have solid state laser, and semiconductor laser. Also, we can have this more advanced gadgets inside this laser device. By instead of the mirrors, you have some other high technique things called like a passive Q switching. It's a dye bleaching kind of mechanism instead of two mirrors. And we have this active Q switch, which we use an electronic control to instead of just two mirrors. So I'm just gonna address some important lasers that I think is we encounter those lasers in our daily life, and I think they are important to us. So first one, helium and neon laser. Helium and neon laser is an example of this 4-level laser, and it's a very simple structure, and it's the first continuous laser here. But because of this helium and neon noble gas here, so in order to have this excited, we have to have a high voltage input. It's just like neon light. We have to really break the thing.
What?
And because of this helium and neon laser is really have this low energy output, so it's really safe. Where we can see that, give an example here, a barcode reader. So this is helium neon laser, gas phase laser. Then we talk about the other gas phase laser, argon ion laser. And this one is also the noble gas inside a gas discharge tube. Because of this is also a noble gas, we still need a very high voltage. And it's the construction is more difficult, more complex than the helium neon laser. But a good thing about this is by changing the different energy pumping or energy input, we can switch the wavelengths of this laser quite easily. And you can see the argon ion laser is really commonly applied to many uses. In, for example, Raman spectroscopy, and they make the holograms possible. And it also is used for entertainment purpose. I don't know if it's a disco or nightclub. I don't go to that kind of places. So yeah, anyway, it's for entertainment purposes. And apparently it has some use in forensic and also optometry surgeries, because use laser to do surgery is a very popular thing these days. It sounds cool and it sounds advanced. It also is used extensively in scientific research or these educational purposes. And the third laser I want to introduce is this carbon dioxide laser here. This laser is really the most efficient and the most efficient laser among all the lasers with the highest efficiency here, and about 30%. And you can see on the picture here, you can actually see nothing because the carbon dioxide laser actually emits the laser beam at a wavelength 10.2 micrometers, so it's not in the visible light range. So you can basically see nothing, but it's really an intense and powerful laser. So it's very commonly used in industrial productions for this cutting and welding. And the low intensity lasers can be used for engraving here. And of course it can be used for some plastic surgery again. And I also read this book, and there's this murder case. Actually someone engineer actually murdered someone else using the carbon dioxide laser, because you cannot really easily trace the laser beam. So suddenly, poof, your head just got fired from nowhere. But it's practically possible. So this is how powerful this CO2 laser is, and it's highly restricted. Or our lab has one. So next one, excimer laser. Excimer laser is excimer is a short term for excited dimer, and the basic mechanism of this excimer laser is you mix noble gas with halide gas together in the chamber, and you excite that, and it has various type of collisions and the reaction here. And when it collides or it forms some metastable state or like the final product, it emits photons in order to reach a stable state. And it's really a high performance laser here. We use this one most often in some surgery, and this is one specific kind of surgery. And at least I know LeBron James did that. If you have this near sight and you don't want to wear glasses, you do the plastic surgery doctors will use the excimer laser to reshape your eye a little bit. Here we go. And lastly, I'm going to talk about a little bit about semiconductor laser. Semiconductor laser is the most important type of laser due to this importance in this optical fiber optic communication these days, and it's gonna continue to be the most important type of laser in the future, and laser, and also the laser research. It's also the future of the laser research, and this semiconductor laser is different from other types of laser because it really just fully use of the characteristic or the semiconductor part of feature of the feature of semiconductors to produce photon by have this electron and hole recombination in the p-n junction to emit this photon. And by doing so, we don't need mirrors to do the oscillation in between. And it's also really the very simple construction here. And because of the semiconductor laser, it has a very small size, so it can fit in many applications. So it's the most commonly used type of laser these days. But it also has some drawbacks because of this semiconductor nature. This type of laser is significantly affected by the temperature. So you have to have a cooling system with it. And if you can't have cooling system besides that, it might cause some problem, or you just can't produce any laser beam. And with that, I'm gonna close out today's talk. I hope you all enjoyed this topic and learn something from that. So, questions? Yeah, go ahead.
Well, you want stimulated emission.
Yeah,
You don't want spontaneous emission.
yeah.
How do you make? I didn't really understand how you make sure that spontaneous emission.
So, before you have a stimulated emission, you have to excite it, these atoms to an excited state. That's why before you have, that's why you have the first step, energy pumping. You have an outside source to charge, to really invest energy to that.
What if it just drops immediately?
No, it has to reach it's a like 3-level or 4-level systems. So eventually, if you keep doing that for a short term of time, I didn't look up the really exact time or the duration, but it's a very short period of time to reach a kind of equilibrium, metastable state. And because we have a third system there, a third level there, so we can hold some of the atoms at that state a little bit longer, so we can reach the population inversion and have this stimulated emission. Any other questions?
So is it polarized because of the direction? Hello. Is it polarized because of the direction it leaves the emitter, or is it polarized because only the waves that curve it go back and forth and back and
the
forth?
last part. It's the optical resonator
Yeah.
between the so you can only have one kind of you have a small slit kind of thing. So you can only leave these mirror through this.
But it's not perfect, right? Like, because eventually even lasers spread out
Yeah,
over
it's-
distance.
Yeah, the divergence you can also see here if you put this one a little bit further away, this thing just spread. So
You point it at the
Yeah.
black wall.
I don't know.
But does it
It gets bigger, a
is it
little
really
bit
bigger, or do we just perceive it? I guess.
It looks
See?
bigger. But
Yeah,
is that
this
caused
is
by like atmosphere or?
Yeah. I don't
It could be
know.
caused by atmosphere.
I think it's because they're not perfect as
Like,
well.
yeah, I guess it's not like-
a little bit of A and a little bit of B.
This one is not like a very precise laser pointer here. This one,
I guess that would, if
this
it's
one
like
is
one
a-
point, it defeat the purpose of
it's
laser
a
pointer.
semiconductor laser here. But by changing material, you can have different wavelengths. Yeah.
So like what would, going off of what Wu-Tan said about the stimulated and spontaneous,
Yeah.
what kind of distinguishes between the two?
Spontaneous emission it occurs like naturally. A stimulated emission, you have to have to meet some requirements. First off, you have to have
Like the
least-
levels, is
yeah.
that what kind of distinguishes
Yeah.
it? Okay.
You have to have your atom already excited to have that. Because instead, if you have a spontaneous emission, it only gets released the energy observed. But by stimulated emission, you not only release the energies already like at excited state gets released, but also the part of the incident photon. You also get transparent, like transparent light bulb. So the energy just gets amplified.
So the metastable state just gives you a delay for the
Yeah.
and for the number of particles to accumulate, so your Boltzmann ratio is too
Yeah.
high. N2 is greater than N1.
Into into higher than one.
And then, like, it's kind of counterintuitive that 2 photons get released instead of 1. Like, is
Is it
that
just one photon?
is it? So go back to the slide where
Yeah.
you have the
That's
keep going, keep going, keep going.
There it is.
I don't know.
Yeah. So on the bottom,
Yeah.
does the energy add up? Like, is this like like thermodynamically impossible, or is it just 2 because it delays for a while and then 2 gets?
It's not thermodynamically impossible because you have to invest energy.
Yeah.
This part, like this energy is here, incident energy, and this part is already excited previously.
Ah.
Okay,
So
that
the light
makes
So
sense.
you're
transfers.
already up.
Because this part is the thing have stimulus emission occurs, and you have these circles here,
Yeah.
and it has this charged input energy into it. It's not like you create energy from nothing.
Yeah.
It has to have this investment here, and the highest efficiency of transforming this energy to this stimulated emission is like 30%, which is the carbon dioxide laser. It's not really efficiency, and people are still working on that. And a fun fact about laser is I actually look up the how many Nobel Prize relate to this part. It's like 8 or something. So the application part of scientific research is more likely, more possible to win your Nobel Prize rather than some theoretical work.
Yeah.
Or fundamental
Yeah.
molecular mechanics.
What did Einstein get?
Photoelectric effect in 1907 or 1906.
That's light on metal, right?
Yeah.
Yeah, it's basically this part. If you have the right amount of energy input, you can actually have this electron beam go excited and fly out of your nucleus.
It's so interesting because it's like physics has almost lost out to biochemistry in the last 20 years. You know, nobody cares about physics, but like.
No, last year was something
Oh, with
with
Nobel Prize even? Oh, okay.
diode or something. I don't recall. Last year's physics, Nobel Prize in physics was given to like 3 Japanese scientists doing all the. Is it chemistry? In chemistry, I guess. Yeah. Was given to diode or something.
And like over 10 years ago, there was a group working on sound lasers. It was really cool. Like, so the idea is that you can, you know, at the UN, beam only the language to that person because it doesn't spread out,
Oh, that's so cool.
right? So you can beam French to one seat and
Yeah.
Swahili to another,
Yeah.
and they wouldn't lose intensity. I don't know how far they got.
Long range secrets.
Yeah.
Yeah, and also it has some military use. And I actually looked up. They were trying to do this thing to do some defense by shine a very intense laser beam to some pilot to blind them temporarily or like permanently.
Yeah. What happened to the laser gun? Because I mean, it's on laser sighting is used on a whole lot of weapons, but like, is it just the energy? It's on
I think the most the charge there is more like if the laser weapon is portable or not, because you have to have a high energy output, and it's not really.
30%.
And then you could fight back with a mirror, right?
Yeah, but if you have very high intensity laser beam, it might just melt.
Melt the mirror.
No, don't we have laser weapons? It's like defensive only though, like to shoot down missiles.
Oh, well,
You beam a missile till it explodes.
Oh, I didn't know that.
I think so. Or maybe that's science fiction.
Maybe we should
Science
try
fiction is just it's a portrait of our future life. So what Star Trek, all those things will be possible.
That's a question. What's a phaser?
Phaser?
Phaser, I'm not quite